Hello everyone. I appreciate all the audience attending this session of building line pay monitoring system and anomaly load detection using ML. My name is Hanuk Kim. I'm a server engineer in the team of fraud detection system. Line pay has gone through a drastic increase in the scale of service in the last few years. Even though we've been trying our best to follow up the speed of growth, the previously used monitoring system are no longer suitable to the current line pay. This session will go over how the new line pay monitoring system has repaid the technical debts inherited from the past. This session will be served by two speakers. In the first part, Gaussian will provide the problem of existing monitoring system and the architecture of new monitoring system and the next step of line pay monitoring. The part number 2 will be served by me. I will start with explaining why we started this project to find the abnormal logs. Then I will continue the session with technical details of how we started applying machine learning into the new monitoring system to find the abnormal logs. Please bear with us. I wish our experience can provide some insight on your future work. Now I'll pass the ball over to Gaussian, who will explain the architecture of line pay monitoring system. I will come back after him.
Hello, I'm Gaussian Lee from Line Pay DevOps team. I'm going to talk about how Line Pay built our own monitoring system. First, I will explain the problems that Line Pay faced in monitoring. As you see, we had various monitoring tools. There are infra resource monitoring system in each country, and log monitoring system, and business monitoring system. Monitoring with various tools had made some problems. First, it is hard to grasp the whole system at a glance. Line Pay members have to visit many systems to find what they want to see. Those are monitoring tools that I used before. I visited them every day. And those have their own alert system. It is hard to control alert because each alert system has different settings and functions. So, it was common for Line Pay members to receive alarm of service previously in charge. And the way of grouping members is different. So, if pay members want to change alarm, they need to change alarm manually at each system. And those monitoring tools are common infra of Line. Of course, the infra of Line is very useful. But when Line Pay has specific requirements about monitoring, it is hard for Line infra team to change the system just for Line Pay. For example, by analyzing past data, we caught that the CPU utilization of one server shows different patterns from same server groups. But infra monitoring system only detects whether the metric exceeds static threshold or not. And there is another example. When services outside Line Pay has problem, the count of Line Pay API decreased. In this case, we can know the count of API in log monitoring system, but log monitoring system cannot catch rapid decrease of API count. Like this, if we have some ways to control metric which already collected, we could detect errors. So we start to build our own monitoring system to solve those problems. This is the structure of new monitoring system, and it is composed of 4 parts. First, collecting metrics. Second, reprocessing metrics and evaluating alerts. Third, managing alarm. And last, visualization. So first, let's see collecting metrics. We insert System Exporter and Application Exporter to collect metrics. System Exporter exposes the resources like CPU or memory usage. And Application Exporter exposes the application resources like garbage collection or thread status. Also, business metrics are also exposed by Application Exporter. And then the metrics are saved in Prometheus. And the logs of application are sent to log collector by log appender. Log appender is our own library to help to send the logs without changing code. We just need to add library and write some XML file. After collecting metrics, it is time to reprocess metrics and evaluate alerts. Flink is stream processing tool. we can make more meaningful information by reprocessing raw metrics. For example, using raw metric about logs, we can calculate the statistic of logs. Or if we apply the abnormal detection module that Sunwook is going to explain soon, we can detect abnormal logs among the stream of logs. Push gateway is a temporal repository to overcome the limit of pool-based collecting of Prometheus. Prometheus can also reprocess metrics, but what Prometheus reprocess is just for reducing calculating time in Grafana. But there is a more important thing in Prometheus, that is creating alert. Using PromQL or Prometheus, we can make more flexible alerts. I will explain it soon with real-world example. And fired alert is sent to Alert Manager. So the next step is managing alarm. Alert Manager groups alerts and manages alert settings. But the most important thing of Alert Manager is mapping alert to service. Alert Manager passes the alert to each service in Alarm Tool. Alarm Tool maps the service to pay member. And finally, Alarm Tool sends alarm to pay member. Dividing alert layer is a big difference from existing system. Previously, the system will make alerts, directly send alarm to pay member. But in this case, if the server is changed or the person in charge of service is changed, we need to fix it manually at all systems. But if we divide a layer like right side, when server is changed, we just need to change alert evaluating layer. And when the team in charge of service is changed, we just need to map the service to new team. The last part is visualization. We use Grafana for visualization. We want one Grafana shows all metric about line pay. Now we learn 3 dashboards. One is Application Overview Dashboard. In here, we can see a server information, server resources, and application resources. And the other one is API Dashboard. It shows the RPS of API, or request duration, or the count by leisure time. The last one is Business Dashboard. It shows some business statistics like the count of registered user in line pay, or the count of top-up or withdrawal. Now, we can make more dashboard if there is a request from line pay. Okay, so let's go back to beginning. I will explain what changed. First, it was hard to grasp the system. This is the monitoring system before, and we can make that simple like this. We decide to use log monitoring system in parallel because searching and showing the logs needs a complex system itself. Second, it was hard to manage alarm. Now, we just send all alerts to new Alarm Tool, and we can easily manage alarm in Alarm Tool. Also, Alarm Tool provides professional functions for alarm. Third, it was hard to handle requirement of line pay. But now, we can handle specific requirement of line pay because we can control all metrics ourselves. For example, as I said before, we want to detect the situation that one server shows different resources pattern with same server group. So we calculate the average of resources of a server group except one server. And by comparing metrics between one server and the average of other servers, we can make alert about this situation. So this is the CPU utilization of one server group. You can see the green line shows the more CPU utilization than other lines. Now we can detect situations like this. And we want to detect rapid change of API requests. In PromQL, there are average function and standard deviation function. And we decide to make alert using average and standard deviation because the slowly changing API moves within a certain range. This graph shows a request per second of an API. The middle green line is current value, and the blue line and the yellow line is dynamic threshold to detect rapid change of API. So if current value exceeds this range for a minute, the alert is fired. And there are many nodes for connection to external system. We can quickly respond to integration with other systems. For example, log monitoring system can request callback API when alert is fired. A new alarm tool has alert API. So we made a connector server that receives alert from log monitoring system and extract data from alerts and send the API to alarm tool. In this way, we integrated the alert of log monitoring system into our monitoring system. Okay, I explained the way to build our own monitoring system. Of course, it is not complete. We have something to do for improvement. We made a lure for common users, and there are a lot of services and servers and APIs in LinePay. And our lure had made some first positive alerts because of these things in slide. So those are our next tasks. I'm going to talk about it a little. When we made a lure initially, we missed that each server have different usage pattern, and we got a lot of first positive alerts. For example, this is a general service server used by user. The resources of this kind of server is changed by user. And this is a batch server which is not used by users. This server do regular batch jobs, and some batch job needs many resources. So the resources of this server is rapidly and regularly changed. And last, this is an admin server which is used by pay member. This server irregularly do some heavy jobs like making or downloading files. So the resources of this server is rapidly but irregularly changed. Currently, lure is divided into general server and admin and batch servers. But the servers need to be more categorized because there are still a few first positive alerts about this problem. Second thing is that servers have different scale of usage. As I said before, we compare the one server and the average of other servers to detect real resources pattern. So when the utilization of one server exceeds n times of the average of other servers, the alert is fired. Then let's suppose n is 2. If the average of CPU utilization of other servers is 25%, then the alert threshold will be 50%. In this situation, the slow API can occur and the alert is fired at right time. But if the average of other server is 5%, then alert threshold is only 10%. In this situation, there's no errors and first positive alarm is fired. So it is hard to make a lure for common users. Last, different pattern of API make me hard to create lures. I said that we use the average and standard deviation to detect rapid change of API. This method works well in frequently requested API, but some API is rarely or regularly requested. And it is hard to apply average and standard deviation to those APIs. I will show you some examples. This API is what we intended. In this case, our alert works well. This API is rarely requested. When the alert about rapid increasing API is fired, but the request per second of this API is just below 1. And this API is regularly called like a batch job. But this API is not in a batch server. So now I excluded this kind of API from alerts. Okay, I explained the next step of LinePay monitoring. As you know, those have same purpose. That is, reducing first positive alerts and making more reliable monitoring system. Next speaker, Sonuk, also have been trying to make reliable monitoring system from first positive alerts. But he has more powerful weapon called machine learning. He will explain how to detect first positive alerts using machine learning. So thank you for listening to my presentation, and it's time to pass the ball to Sonuk again. Thank you.
Hello, I'm back to serve this session. In the previous session, Gising nicely explained how LinePay adopts new monitoring system. One of the great positive effects of new monitoring system is that we now sell the infrastructure to initiate a new data-driven project. In this session, I'll share the journey of how we started utilizing machine learning to find abnormal log inside the LinePay. Let's go over where the need of this project originated from. LinePay has gone through a drastic increase in the scale of service in the last few years. The table on the right demonstrates monthly summary of current LinePay log. We are currently utilizing about 400 kinds of API and 200 kinds of return code. About 10 million occurrences of errors are found on each month. However, this tremendous amount of errors are no longer related to actual outage situations. The false alarm from this error started to increase the fatigue of system engineers and managers. We've been dodging this situation with superficial methods such as turning off error alarms from particular APIs. The following solution eventually lowered the awareness on the true positive errors, like real outage situations. Therefore, we set our goal to reverse this situation. We aim to develop a system working as a middleman, which can decrease in the amount of false positive, and therefore lessening the fatigue of engineers and increase the awareness to the true positives. I'd like to draw an analogy between our goal and weather forecast system. When we have to commute to the work tomorrow, and there is 70% chance of raining according to the weather forecast, we wake up in the morning on the day after and found out that it is not raining yet. But we all have a habit to open the window, check the clouds in the sky, and smell the humidity of air to make a decision by ourselves if we have to bring the umbrella to the work. Likewise, we aim to build a log forecast system to warn possible outage situation in near future to the engineers. We investigate on the history of outage to formulate hypotheses. About 45% of errors were shown when there is some kind of change in the request, such as increase in the request count or response time. Secondly, the change in the log message flow were in charge of 35% of errors. Other errors were related to system statistics, such as garbage collection and heap memories. Based on this investigation, we brought on two hypotheses. First, sudden increase in a particular API request indicates an early signal of outage. Second, tangled sequence of log can be an omen of outage. Based on these two hypotheses, we started to select machine learning models. We have some prerequisite conditions on the selection of models. First, it has to be an unsupervised learning, because there is no way we could filter out and label anomalies from the millions of log. Second, model has to be robust to retraining. LinePay frequently applies new features and APIs to follow up the user's need. If the model is fragile to the frequent change, the model will turn into a mess in the future. Third, the model has to be fast enough to endure the load of LinePay logs occurring about 1,000 times in a second. Next, the model also has to provide some way to find the root cause of the result. As I mentioned in the earlier of this session, our goal is to warn possible outage situation. That is, final decision has to be made by developers based on the reference offered by the model's result. Lastly, it is our first step of applying machine learning since new LinePay monitoring system is set. Therefore, we prefer a model that is simple so that we can implement it in a brief period of time. Based on this essential condition, we finalized two models, which are Gaussian mixture model for hypothesis 1 and LSTM model with workflow for hypothesis 2. I'm assuming audience who has no knowledge of machine learning. So allow me to briefly introduce what Gaussian mixture model is. Without the knowledge of machine learning, I'm pretty sure that we are all familiar with this bell-shaped curve, which is called Gaussian distribution or normal distribution. This curve could be drawn if mean and standard deviation of data are known. If given data have a distribution of Gaussian, we could say that the data on the edge of distribution are abnormal compared to the others. This is an example showing a data distribution fitted with 3 Gaussians. Abnormal data that are deviate from the center are marked as red stars. Those audience who has many experience with machine learning should agree that Gaussian mixture model is simple, but very powerful and efficient algorithm if we could find a feature having a shape of Gaussian inside the data. The fourth feature we selected was the rate, that is number of log having same API ID and return code out of total API count within specific time frames. We selected 3 time frames of 5 minute, 10 minute, and 30 minute because they seem to show the best fit with Gaussian distribution with durable processing time. As you can see in this chart, plotting the feature of each API, they seem to represent their own Gaussian distribution. This graph shows that the aggregate data are fit into 2 Gaussian distributions with a cluster of anomalies. When I first found this distribution, I thought that this feature might have a chance of good result if a little bit of tuning is applied. However, this feature has some critical flaw in the result. First, this feature required expensive processing time. When I started this project, I first thought that the goal of this project is finding an abnormal log. This thought led me to process each log to decide its anomaly, and this was a big mistake. It takes a couple of seconds to convert each log into a feature, and the conversion time resulted into a massive processing time with thousands of error code occurring per second. Second, each API feature has similar but different distribution. The cluster on the bottom left are jumbled distribution of many API features that are fit into one Gaussian distribution. As a result, the abnormal log came out from only few specific type of APIs that had a wider and flatter distribution than others. Third, the number of API count was highly biased to few specific types of API. 3 kinds of API dominate about 50% of total APIs. This problem also gave rise to biased abnormal log in the result. Lastly, this feature was vulnerable to retraining. About 400 of API had their own distributions. If 400 kinds of Gaussian distribution are fitted individually to each API, the model has to be retrained whenever new API is added. This is definitely not a way we expected. We started seeking for a new solution. The solution of this problem was straightforward. We just need to discover a new feature that can cover all the problems mentioned on the previous page. The newly designed feature is the rate of increase in API count. The logs are grouped by API ID and return code within given time window. Each feature is the percent increase of log count from the previous time to current window. The feature could resolve the challenge we faced. First, the feature can save a lot of processing time. This feature only needs to be calculated every 30 minutes in a batch operation. The big difference of this feature is that we started looking for an abnormal zone instead of abnormal log. The second advantage of this feature is that it can draw the individual distribution into one single distribution. The rate of increase can be shared no matter what API types are. Using this feature, there will be no need to retrain the model even if a new API is added. The graph on the left is the result that all the features are fitted into one Gaussian distribution. The abnormal log in the third quadrant are excluded because we are only looking for increase in the request counts. The scatter plot on the right indicates a normal log as sky blue and abnormal log as cyan in a chronological sequence. As you can see, the abnormal log from the feature are regularly distributed in time. The output of this model looked fine at first, but we realized that minor challenges have to be tuned to apply this model to real situation. Let's go over what the another challenge we faced were. The second challenge was the batch process. As you can see on this plot, LinePay operates a couple of daily batches to process transactions. The number of errors from the batch are proportional to the number of transactions it has to process on the day. However, the errors from the batch is not a situation we are looking for. Even though the batch error possibly includes the abnormal logs when there is a radical increase compared to the previous day, the situation that every batch error are selected as an abnormal log had to be excluded from the result. The solution to resolve this challenge was pretty simple. If the occurrence of errors are empty on the next following feature, the empty feature was replaced with the previous feature value. The fine-tuning of this feature could minimize the periodical sudden increase from the batch process. This feature could eliminate 90% of batch anomalies, and as a result, we could be able to see a wide variety of anomalies from different types of APIs. The third challenge we faced was that this model still could not take care of anomalies from the minor type of APIs. For example, this plot shows an abnormal increase of errors. This error occurred once, at this time only, in this month. And this situation was related to actual outage. However, if this plot is zoomed into a narrower interval, the occurrence of errors are steady and tiny. I realized that my previous assumption on the feature was wrong. For example, I first expected that lightly used API would increase from 1 to 100. That is a 100% increase. Likewise, I also expected that heavily used API would increase from 100 to 10 million. That is also a 100% of increase. However, the actual behavior of errors are all different. Lightly used API increased from 1 to 100, while heavily used API increased from 1 to 10,000, which is 10,000% of increase. Therefore, we should seek for a solution that could balance out the increase between lightly used API and heavily used API. The third challenge could be overcome by two kinds of fixes. First, we applied penalty on the future value based on its amount of usage. The penalty was calculated as a complementary value of the rate of each API usage. The penalty was simply multiplied to the future value, so the highly used API feature gets a big reduction, while lightly used API feature gets insignificant reduction. The second tuning was the adding more features. We utilized more features of weekly and monthly trend compared to the current count. By doing this lightly and rarely occurring error could get extra scores on the result, while heavily and frequently occurring error get marginal point from the new features. The model with these fixes could return the balanced output we are looking for. This is a brief summary of Gaussian mixture model result. The 10 million error alarms could be narrowed down to 500 anomalies. The abnormal result included about 30 types of API out of 400 kinds of API. And then we applied few post-processing to the result. For example, the consecutively occurring error were merged into one error. The result from few APIs that we could possibly ignore the risk was eliminated. As a result, the final abnormal error alarms could fall below 150 error. And this error included about 15% of actual outage situations. Now, let's move on to our next model. Our second model is LSTM, which stands for Long Short-Term Memory. Again, let me briefly introduce the summary of what LSTM is, to help understanding of people who are not familiar with machine learning. I will not demonstrate the technical detail of LSTM today, but just an intuitional insight of LSTM. Let's say I've been a close friend with Gaussian from childhood. I've had many chances to play rock, scissors, paper game with him. That is, my brain already experienced many patterns of his move. We choose to play rock, scissors, paper today to decide the opening speaker of this session. He has shown a pattern of rock, scissors, scissors, rock, and scissors in the game. And based on the information of his pattern I have, I can expect that there is very high probability that he will show a scissors again on the next move. This is basically how LSTM is designed. LSTM is a type of recurrent neural network architecture capable of running order dependency in sequence prediction problems. LSTM is applicable to the variety of tasks such as speech recognition, sentence autocomplete, and time series anomaly detection. Looking at a short-term memory, it utilized its history of long-term memory to predict next output. Let me give you a couple of more examples. We have seen a word autocomplete functionality on the cell phone. If I write a character H, E, L, L in a sequence, the model can predict that the character that might come out on the next is O. Also, if I browse a sentence until how to make delicious, the search engine returns a list of next possible word in an order of high probability. Just like the examples on the previous page, let's say we have a sequence of log where the numbers represent the types of each log. One of the strong advantages of LSTM is that even though LSTM is a supervised learning algorithm, we can start training the model as if it is an unsupervised learning without any labeled data. And the model can be updated with labeled data by System Manager later. For example, LSTM can be trained with sliding windows. If the window size is 4, the fifth component will be the label of the training data. After the model is trained successfully with a sequence of log, the input of the model will also be a sequence of log having same size window. Then the model will return the possible outputs of next component in an order of high probability. If the actual log occurred after sequence is not included in the list of predicted components from the model, we could say that the current log is abnormal. Let's dive into the architectural flow of our model. This flowchart has two components, training stage and detection stage. Starting from the left side, we have a bunch of raw logs prepared for training. The logs are parsed into unique template and are assigned its template numbers. The output of the parser is just a series of template numbers. And then this group of numbers are converted into sequence vectors and count vector, which are appropriate feature to train LSTM model. On the detection stage, the trained model takes a history of recent sequence of log as an input, and the model returns the probability distribution of all possible template values. If the actual log is not included in the highest rank template, the model alerts the system manager about these anomalies. The system manager makes a decision if the log is false positive or true positive. If the manager assigns it as a true positive, the corresponding sequence of data is used to update model online with labeling it as an anomaly. We had one challenge from this model. LinePay operates multiple server and tasks simultaneously. Therefore, same log template may appear in more than one task, and concurrency is possible within each task. The concurrently running thread inside each task leads uncertainty in the ordering of log message corresponding to one task. Even though the model itself can encode the underlying execution path, there were some difficulties understanding the result from the model to decide its anomalies when concurrency plays into a sequence of log. Therefore, our goal is to separate log entry for different tasks in a log file and then build a workflow model for each task based on its sequence. To solve this problem, we take a reference from a paper called dimlog. The order of log entry produced by a task represents an execution order of each function to accomplish the task. As a result, we can build a workflow model as a finite state automaton to capture the execution path of any task. The challenge is to find a divergence point of whether the multi-key prediction output is caused by either concurrency in the same task or the start of different tasks. The divergence point of concurrency and new task shows a clear difference in the sequence of log. A common pattern of concurrency is that keys with the highest probability in the prediction output will appear one after another. And the certainty for the following prediction will increase as the keys for the sum of concurrent threads have already appeared. On the other hand, if divergence point is caused by the start of a new task, the predicted log key will not appear one after another. If we incorporate each log key into the history of sequence, the next prediction is a deterministic prediction of a new log key. If this is the case, the work model of the current task stops growing its branch. And then the constructed workflow are saved into workflow library at the end. As a result, By the side of LSTM model, this workflow model plays a key role, offering a reference to make a decision of its anomalies from the result. We could retrieve some valuable results from these models. Before I go over what they were, I ask for understanding that I could not share the details of the result for security reasons. Let's briefly go over what the results were. First, there were very trivial errors occurring many times, such as token errors or service maintenance. These errors were not directly related to the outage situations. There were other cases we have to have questions on it. There were a sudden increase of requests from particular users. The amount of increase was not definitely possible by the speed of human being. This could be a try-of attack or problems in the client side. The other case could be seen in the case of account log. When the shared resources of LinePay are swamped with multiple simultaneous requests, there are a trend of fast increase in the errors. For example, when a multiple payment is requested to one account at the same time, the account is locked to process a single transaction and the other cases are failed with errors. This case could also be a possible signal of outage. Additionally, the result also included the signal of possible server outage such as memory errors and connection failure. Lastly, the model also returns the case when it saw a new message it has never seen before. This is it for today's session. Thank you for patiently listening. I wish I could deliver another technological review in near future, face-to-face, after the era of COVID-19 is over. Thank you very much.